Hey, Wheaton North Chemistry students, Mrs. Terada here. Today I'm going to talk to you about nuclear charge and shielding, two phenomena that happen inside the nucleus, inside the atom. Hey, Wheaton North Chemistry students, Mrs. Terada here. Today I'm going to talk to you about nuclear charge and shielding, two phenomena that happen inside the atom. First off is nuclear charge. This is the charge of the nucleus. So the things in the nucleus that have a charge are the protons. Those positive protons will attract negative electrons. So the positive protons are creating an attractive force on every single electron in the atom. The electrons that we're going to focus on pretty much for the rest of the year are the outermost electrons, the valence electrons. So those attractive forces from the protons in the nucleus pulling the valence electrons towards the nucleus is the nuclear charge. The more protons an atom has, the stronger that attractive force. As you can see from the picture, there is a As you can see from the picture, there is a counter force in play, and that's what we call shielding. Those negative electrons all repel each other. So the inner electrons are repelling the outer electrons and pushing them away. So it's counteracting that attractive force. We call these inner electrons shields. They're protecting the valence electron from the nuclear charge. The more inner energy levels you have, the more shields you have counteracting the attractive force. Mr. Yergler has a great analogy for us that he made last year that we're going to listen to.
A good analogy is music concerts. This guy right here is Andrea Bocelli. He's an opera singer. I went to a concert and sat in the very front row at the concert. So there was literally no shielding. I got the full effect of the music, the full effect of the speakers, the stage, and all of that. He's got a great voice. Google him if you've never heard of him. Okay, now if we want to go to a different concert, maybe Taylor Swift, for example. I've never been to a T Swift concert, but wouldn't mind going, I suppose. And whoever took this picture is kind of partially shielded, right? There's quite a few people in between the person and the stage, and so the music, the effect of the music, the speakers, the volume, all of those things are somewhat shielded by these other people that are in between the stage and the observer, or the person taking the picture. If we look at another example, this is a bunch of people waiting for a Mumford & Sons concert. If we look at this guy right here, he is very, very shielded from the stage. There's a lot of people in between him, right? And it looks like it's a flat ground, so you probably can't really see the stage at all, which kind of explains why he's bored and looking at his cell phone. So if he was an electron and the stage is the nucleus, then the effect of the stage, or the effect of the nucleus's pull, is being kind of absorbed or kind of shielded by all these people in between him and the nucleus, or him and the stage, right? So this analogy kind of helps to understand why this happens, but it's a little off because it doesn't exactly describe how it happens. In the analogy, in the music concert analogy, these people are kind of absorbing or blocking the sound from the stage, but in an atom, it kind of acts a little bit differently, or kind of happens a little bit differently. So let's go back to the atom. Here's a zoomed in picture of an atom. Here we have the nucleus, which would be positive, and the negative electrons. Now, in the stage analogy, or the music analogy, this attraction force is kind of absorbed or blocked by the other people in the concert, or in the auditorium. That's not really happening in an atom. This electron is still getting the full effect of the nucleus. It's the full attraction force. However, there are other forces at play. When you have electrons in between that outside electron and the nucleus, remember that all the electrons are negative, so they're going to repel each other constantly. So every electron is repelling every other electron. And so the total force, you could say, is decreased because you have these repulsion forces pushing back on the electron, and then you have the attraction force that is always there, always felt. If we want to look at two two similar atoms, sodium and potassium, and there's also a picture of lithium here. These are all in group 1, I believe. And so they're very similar in reactivity, but potassium is more reactive than sodium. And the reason that this is the case is because of shielding. So if you look at these two electrons right here, which one is more shielded? There's a lot more electrons in between this electron and its nucleus than there are between this electron and its nucleus, right? There's a whole other ring of electrons. And so this electron is a lot more shielded than this electron is. And that makes it a lot easier to remove because there's more repulsion forces from these other electrons pushing away on that electron. And so this electron would be easier to be removed from that atom and go and bond with something else. And when electrons leave and when they come and attach to other atoms, whenever electrons are moving, you typically have chemical reactions, right? And potassium is a lot more reactive than sodium because that outside electron is so much easier to remove than sodium's outside electron.
All right, thanks, Mr. Yergler. One last thing, another way to kind of figure out how those two forces are interacting is something called the effective nuclear charge. If you take the total number of protons in an atom and you subtract the number of electrons that are providing that shielding repulsion effect, so if you look at this phosphorus atom, we've got 15 protons. That's what we're going to start with. That's our attractive force. And we subtract the counterbalancing forces, the repulsion forces of the inner electrons. So we have our first shield with 2 electrons. We have our second shield with 8 electrons. So we subtract 10. That'll give us an effective nuclear charge of +5. When you're comparing atoms, like Mr. Yergler was doing in the video, you can figure out the effective nuclear charge of both of them, and you'll see that atoms with a larger effective nuclear charge have a greater pull on the valence electrons, thus making it harder to steal those electrons away. So again, we're going to get more into that in the next couple of videos, but hopefully nuclear charge and shielding you've got a good handle on and you can apply them in your next worksheets. Good luck!